Okay, now we're going to go further and look at acetals, which add another alcohol to a carbonyl. I'm going to start with cyclohexanone and treat it with two equivalents of methanol and H3O+. And the net result is that, once again, this carbonyl breaks, and you end up with two methoxy groups attached at the same position as the carbonyl plus water. What happens with this is now we actually have hidden the C double bond O, or hidden the electrophilic carbon underneath these two methoxy groups. So in essence, acetal works to be a protecting group. So say you have a compound like this, and you have, and I'm just doing this as an example, you have two different places where you have an electrophilic carbon. This carbon is electrophilic, and this carbon is electrophilic. And you want to run a reaction, say an SN2 reaction, where the nucleophile would attack in either place. If you use an acetal, what happens is you can take and hide this electrophilic carbon underneath an acetal and be able to, oh, that was ugly, sorry about that, and be able to get rid of it, in essence, and then do your reaction on the other electrophile, and then unzip it, and then take this off. So acetals are used as protecting groups. Now I'm going to just clean up my desk right here. There we go. And we're going to run through this mechanism. And it's pretty long, so give yourself a little space when you draw. And it runs through very similar to the hemiacetal mechanism from the previous video. So first step is always to protonate your O and make that oxygen more electrophilic. We know where we're going. We're going to have to add two nucleophiles here. So the next step is our protonated ketone. And then methanol comes in and attacks at the electrophilic carbon. And then we have OH and OHCH3 with a plus. Now, this is where I cheat a little bit. What you need to do is create this as a leaving group. Here's your water. I do this as a proton relay. By probably this O gets protonated by hydronium that's floating around, but since it's right there, it's sort of a cheater's way of not having to redraw, and this is what I call the proton relay. But in essence, what we're trying to get at is getting that OH to be a good leaving group, because OH will not leave as OH in an acid environment. It has to leave as water. And so now we have this. Now, there are two different philosophies here. A lot of my students like to just draw the leaving group leaving. I tend to draw it this way, so the leaving group gets pushed. Either way, what you're going to get is you're going to get this structure here, which looks a lot like this one. Or if you just do this arrow here without forming the double bond, you are just making this resonance structure. And sometimes my students tend to like this because they can see the plus right there. It's the same thing because they're resonance structures. So the next step is our second methanol to come in. And I'm going to use my resonance structure here. The net result then will be your OCH3 on one side, and we're actually one step away from being done here. And so you have your protonated acetone, or protonated methoxy group, and that removes the H plus and regenerates the catalyst. So that is forming an acetal. Now, many times you don't use methanol when you do this reaction. You have a tethered diol such as ethylene glycol. And the net result of this is you have this product. So this is the protecting group, and again, you lose water in the process. You should be able to, just as we did with the hemiacetals, go both forwards and backwards the mechanism. And this mechanism is a really good mechanism to understand as you go through. Once you get all these nucleophilic attacks, deprotonation, leaving group leaves, you really understand mechanisms. So take this mechanism right here that I just did and run it back the other way. Pause your video, try it, and then I will show you again how to do that. Okay, so let's go backwards. Here's our acetal. Remember, anytime you have a carbon attached to two O's at the same time, that's going to become the C double bond O. So here's our C double bond O. And the water comes in to make that O, and you lose two methanols. So now we know where we're going. Go through the mechanism. You're going to take your hydronium and protonate one of the oxygens, redraw. What we just did is create a leaving group. Oops, I switched that around, but you should be able to understand what I just did. OCH3. Now, again, my philosophy is making the leaving group leave by pushing it, creating an electrophilic carbon, and then I just lost the water. Okay, no, I lost the methanol. Sorry about that. Let's erase that. So there's one of our methanols. And then in comes our water. You have an OCH3 and a protonated alcohol. And this is my cheating way. I'm doing my little proton relay. Probably comes from external source, but I'm going to do it this way just because it cuts one drawing down. And now we have our second methanol as a leaving group. And so once again, I push it, and you end up with your protonated ketone. And we've just lost our second methanol. And the last step is the water that came in with the catalyst regenerates the H3O plus. Now, I'm going to show you a really fun little problem, and you have to, I'm going to draw it, and I'd like you to try to figure out what acetal and alcohol is formed. So, oh, that's ugly. I can't stand it when I don't draw it pretty. So we need to have this structure here. I'm going to put an O there, a methyl group here. Probably one of my favorite acetal problems in my book. Looks like that. And what you want to do is treat that with water and H3O plus and figure out what compound comes out of that. I would pause the video right now, think about it, and then come back and I'll show you how to solve this if you didn't already. Or if you did, you'll see that you're right. Okay, I hope you paused, but here we go. This carbon right here is the carbon with the two O's. This is the carbon that's going to become the C double bond O. It always helps to number. So 1, 2, 3, 4, 5, 6, 7. You have to have a total of 7 carbons when you're done. I'm going to unzip this ring. 1, 2. The carbon that has the two O's attached becomes the C double bond O. These two O's end up with H's on them, so they end up as the alcohols. 1, 2, 3, 4, 5, 6, 3, 4, 5, 6, and 6 will have an OH on it, 7, and then 7 will have an OH on it. So if you look, here are the two alcohols. They're tethered together and they close the ring to make this nice little 6-membered ring and then a 5-membered ring. And you should be able to do the mechanism going forward and backwards. So that is how we finish with our acetals.